Hey everyone, Mr. Hauk here. In today's video, we're going to be looking at graphing transformations of secant, cosecant, and cotangent functions given an equation and giving an equation given a graph. Let's go ahead and get started here. So when we talk about graphing transformations of secant and cosecant functions, one of the following procedure is usually pretty helpful. One, we can go ahead and graph transformations onto the appropriate reciprocal trig function. So for example, if we're trying to graph a transformation of secant, we'll use cosine. If we're trying to graph a transformation of cosecant, we'll use sine. It says here in the notes if we're trying to graph a transformation of cotangent to use tangent, but it's actually easier to just go ahead and use cotangent without trying to think about the graph of tangent first. We know that from the previous video that if we have any zeros on, for say, a cosine function, then those zeros would turn into the asymptotes for a secant function. So we're going to use any zeros to make asymptotes for the function we're trying to graph. And then we're going to essentially turn the rest of the graph inside out, at least for secant and cosecant. So let's go ahead and look at this example to get an idea of what's happening here. So we're going to try to graph y equals 2 secant of x minus pi over 4. And when we think about this, the reciprocal of secant is going to be cosine. So we want to try to graph, and let's see, we'll do this in, I guess purple is an okay color. We want to try to graph y equals 2 cosine of x minus pi over 4. So we're taking the transformations that we're trying to apply to secant, and we're going to apply them to secant's reciprocal trig functions instead. So one helpful way to graph, I've been thinking about, maybe some ways to make graphing a little easier for some people, is to do it through a table method. So let's go ahead and consider what cosine would normally look like. Okay, so cosine typically, let's think about some good points for cosine. So some really easy points to plot would be 0, pi over 2, pi, 3 pi over 2, and 2 pi. And we know for cosine that cosine starts at 0, 1. By the time cosine, at pi over 2, the cosine is 0. At pi, the cosine is negative 1. At 3 pi over 2, the cosine is 0. And at 2 pi, the cosine is positive 1. So this is for the parent function of cosine. Now let's think about the transformations that are happening. We have this 2 that's being multiplied, and we have a phase shift of right by pi over 4. Okay, so there's a couple things that we can do. Number one, we know that we can take all of these values, this is where cosine is starting, and we can shift all of these values right by pi over 2. So I'm going to put a little right, or sorry, not by pi over 2, but by pi over 4. So right by pi over 4. So if I shift 0 to the right by pi over 4, I'm going to get pi over 4. If I take pi over 2, so I'm going to put a little arrow here. If I take pi over 2 and I shift it to the right by pi over 4, then I'm going to get 3 pi over 4. If I take pi and shift it to the right by pi over 4, I'm going to get 5 pi over 4. If I take 3 pi over 2 and shift it to the right by pi over 4, I'm going to get 7 pi over 4. And if I take 2 pi and shift it to the right by pi over 4, I'm going to get 9 pi over 4. So this will give me the new x coordinates, okay? And then we also have this, the function values being multiplied by 2. So these right here represent the original function values. Let's go ahead and multiply them by 2. So times 2. So 1 times 2, that'll give us a 2. 0 times 2 would give us 0. Negative 1 times 2 would give us negative 2. 0 times 2 is 0. 1 times 2 is 2. So essentially, our new x values will be right here. Our new y values will be right here. And we're trying to graph the cosine first, and then we're going to take all of the zeros, and we're going to make them asymptotes for secant. Nope, go back. And then we're going to essentially flip the cosine graph inside out. So let's go ahead and graph this 2 cosine of x minus pi over 4. So at pi over 4, we go up to 2. At 3 pi over 4, we go to 0. At 5 pi over 4, we go to negative 2. 7 pi over 4, we're going to go to 0. And then 9 pi over 4, we're going to positive 2. And we could continue the pattern here. We know that a negative pi over 4 would be a 0 also. Okay, so let's go ahead and I'm going to do this in a little dashed line just because this isn't the official graph. So this is our cosine graph to guide us as to what we're going to do with the secant graph. Okay, so like we were saying, any zeros would be asymptotes for the secant graph. So let's graph the secant graph in black here. So everywhere we see an x-intercept or a 0, we're going to go and put an asymptote. So I'm going to put asymptotes here to all the zeros. And then recall from the previous video that any maximum of cosine would turn into a minimum for that section of the secant graph. And any minimum for cosine would turn into a maximum for that section of the secant graph. And here in black, we have the graph for 2 secant of x minus pi over 4. Now let's compare it on Desmos here. So luckily, I already have some of these graphed. So 2 secant x minus pi over 4. And let's just look for some common points here. We're looking for pi over 4, comma 2. There's pi over 4, comma 2. We're looking for 3 pi over 4, 0. We can see that right there. We're looking for 5 pi over 4, negative 2. We can see that right there. And then lastly, let's look at 9 pi over 4, positive 2. We can see that here. So our graph is accurate and everything checks out. And we can move on. Okay. Let's try another example. So this time we're looking at y equals cosecant of 3x plus 1. And thinking about this one, well, the reciprocal of cosecant is going to be sine. So let's go ahead and graph, or let's go ahead and think we want to graph y equals sine of 3x plus 1. Okay, well, let's think about what the parent function of sine looks like. So typically we have sine here. Let's make a little table. That looks bad. Let's try that again. Still looks terrible. One more time. There we go. Okay. So let's pick those same 5 points. Let's pick 0, pi over 2, pi, 3 pi over 2, and 2 pi. These are 5 really good points because they give us really easy function values to work with. So usually sine starts at the origin, 0, 0. At pi over 2, sine goes to 1. At pi, sine goes back to 0. At 3 pi over 2, sine goes to negative 1. And at 2 pi, sine goes to 0. Now let's think about the transformations that are being applied here. So we have this plus 1, which is going to be a vertical shift up 1. So I know the function values are going to end up moving up 1. And we also have this 3 being multiplied to the x. So remember what this is doing is it's essentially taking the period, which is normally 2 pi, and it's dividing the period by 3. So essentially we're getting 3 times as many cycles as sine would normally have with sine of 3x. So essentially what that's doing is it's taking all these original x values and it's dividing them by 3. So I'm going to put a little divided by 3 here. So 0 divided by 3, that's still 0. Pi over 2 divided by 3, that's going to be pi over 6. Pi divided by 3, pi over 3. 3 pi over 2 divided by 3 would be pi over 2. And then 2 pi divided by 3 would just be 2 pi over 3. Okay, now let's take all these function values and let's add 1 to them, shift them up 1. So if I shift 0 up 1, I go to 1. If I shift 1 up 1, I go to 2. If I shift 0 up 1, I go to 1. If I shift negative 1 up 1, that goes to 0. And if I shift 0 up 1, that goes to 1. So now we have our new x-coordinates right here. We have our new y-coordinates right here. This will be the transformation. Y equals sine of 3x plus 1. Let's go ahead and plot those points. So we have 0, 1. We have pi over 6, 2. We have pi over 3, 1. Pi over 2, 0. 2 pi over 3, 1. And we can see this pattern that's going to continue. Okay, so let's just go ahead and fill out the rest with this pattern. Okay, and once again, since this is just the sine of 3x plus 1, let's go ahead and kind of map it out here. Doing this in a dashed line because again, this isn't going to be the our final answer for the graph. This isn't going to be the cosecant of 3x plus 1, but it's going to be kind of our guiding points to where we flip everything inside out. Now, originally, the instructions are take the zeros of sine of 3x plus 1, and those become the asymptotes. Now remember that sine of 3x plus 1 took the original parent function and shifted it up by 1. So the midline is really right here for that sine of 3x plus 1. So we want to take all of these points here, and these become our asymptotes, because these, if we hadn't shifted it up by 1, would have been down here on the x-axis. Those would have been our zeros. Let's go ahead and turn each one of those into an asymptote. So asymptote here, asymptote here, here. You're going to see we're going to get quite a few asymptotes. Okay, so like I said, a lot of asymptotes. And let's go ahead and start turning the graph inside out. So here's a maximum for the sine function. Get that. Here's a minimum. Here's a maximum. Minimum. Maximum. Minimum. And so on. Okay, and that's going to be our graph of y equals cosecant 3x plus 1. And again, let's go ahead and check with Desmos here. So just to save us a little bit of time, I went ahead and graphed cosecant 3x plus 1. And let's just check a few points. Let's check. There's negative pi over 2 comma 2. Here is negative pi over 6, 0. We can see that right here. We got pi over, let's go ahead and hide that one. There's pi over 6, 2. We see that right there. So we can definitely tell that this is the correct graph. All right, let's look at cotangent. So as I mentioned earlier, we're not going to go ahead and graph tangent and then try to change things around for cotangent. Cotangent and tangent are similar enough to where we can really just worry about cotangent here. So let's think about the parent function of cotangent real quick. So think about cotangent. Let's change that. Think about cotangent and cotangent. Let's think about some common points. So we discussed these common points on in the last video. So we know at 0, cotangent's undefined due to a vertical asymptote. We know at pi over 4, cotangent is at positive 1. At pi over 2, cotangent's at 0. At 3 pi over 4, cotangent's at negative 1. And at pi, we are back at undefined due to another vertical asymptote. So let's think about the transformations that are happening here. We have this times 2 out front, so I'll put a little times 2 here. All the function values are going to get multiplied by 2. And then we have this 2 on the inside, which is affecting the period. It's essentially taking all the original points, and we're cutting the period in half, so all these original points are going to get divided by 2, because there's going to be twice as many cycles, so the period's getting cut in half essentially. So I'll put a little divided by 2 right here. So 0 divided by 2 is still 0. Pi over 4 divided by 2 is pi over 8. Pi over 2 divided by 2 is pi over 4. 3 pi over 4 divided by 2 is 3 pi over 8. And pi divided by 2 is pi over 2. Now let's take all these y values right here and multiply them by 2. Well, undefined, you can't multiply it. 1 times 2 is 2, 0 times 2 is 0, negative 1 times 2 is negative 2, and undefined is still going to be undefined. So let's go ahead and graph these here. We can see that we're going to have, due to the undefined, we're going to have an asymptote of 0, so let's go ahead and put an asymptote there. And we're going to have an asymptote at pi over 2. And we can see here that from 0 to pi over 2, we can tell where the other asymptotes are going to be. So let's go ahead and put the other asymptotes in. 3 pi over 2, 2 pi here, 5 pi over 2. And we can put an asymptote here just to kind of continue the pattern. All right, let's go ahead and put in some of these points. So at pi over 8, and pi over 8 is going to be right here, halfway between 0 and pi over 4. So at pi over 8, the y value is at 2. At pi over 4, the y value is at 0. At 3 pi over 8, which is going to be here between pi over 4 and pi over 2, so at 3 pi over 8, we are at negative 2. And then at pi over 2, we're back at undefined. So we can see that we have that shape right there. And let's go ahead and fill in all the other cycles. So here, here, here. Notice that in between all the asymptotes, we have these points in the middle. And we can go ahead and follow the pattern here, halfway between an asymptote and the middle point. Here and here, here and here. And let's sketch in our curves. All right, and there's our graph of y equals 2 cotangent of 2x. Once again, let's check a few points real quickly in Desmos. So here's 2 cotangent of 2x. And let's just look for some common points here. We have pi over 4, 0. We have 3 pi over 4, 0. We have 5 pi over 4, 0. We have 7 pi over 4, 0. We can see all these points are matching up. We don't need to keep checking everything. Everything's looking good there. All right, so this is how we can take, for these last 3 examples, how we can take a graph or an equation and use a table to help create the graph. In the case of secant and cosecant, we're applying the transformation to the reciprocal functions and then turning that function inside out. For cotangent, we can just use some knowledge of the parent cotangent function and apply transformations to that. Now let's kind of do the opposite. So now we're going to be given a graph and we want to figure out what the original equation was for that trig function. So let's think about kind of what's happening here. First things first is I want to figure out what kind of function I'm going to be using. And notice that if I go ahead and put in some guiding points here, so I'm going to put some points right here. And we know that for these kind of functions, whether it's secant or cosecant, we can see the asymptotes. So let's put in the asymptotes. And we know those asymptotes would have been the locations of zeros for the reciprocal trig function. So one thing I'm noticing, though, is that the midline is not at the x-axis. The midline has been shifted up to positive 1. So that already tells me, so let's go ahead and write that down, midline is at y equals 1. So that already tells me there's been a vertical shift up 1. Okay, so that's going to be pretty important. The other thing I'm noticing, and let's go ahead and fill in what the reciprocal trig function would look like. So I would have something like this. Okay, so I can also tell the amplitude here, because if the midline is at y equals 1, that goes up 1 to a maximum, or it goes down 1 from the midline to a minimum. So the amplitude, remained a positive 1. The amplitude did not get larger. So A is going to be equal to 1. Another thing we can go ahead and identify is the period. So we can see that the period takes from 0 to 4 pi, so the period is 4 pi. And if we think about sine and cosine, the period, which in this case is 4 pi, will always be equal to 2 pi divided by the b term. Well, in order to get a period of 4 pi, b is going to have to be equal to 1/2. So we know the b term is 1/2. Now let's think about what parent function we want to use. Well, notice that we have a maximum here on the y-axis. If we have a maximum on the y-axis, we're going to want to use cosine. We know that because sine goes through the origin. So we're going to want to use cosine here. So let's think about what these transformations are looking like. Our a term is 1, so nothing being multiplied out front. Our b term is 1/2, so we have 1/2 x, or x over 2. And the midline was moved up 1, so we know there was a vertical shift plus 1. So that's representing, again, this dashed line here. And these are the transformations that got applied. So all we have to do is take these transformations, and thinking about cosine, well, the reciprocal of cosine is secant. So the function that we're looking for, this function in blue, is this. Y equals secant x over 2 plus 1. And this is the function that we are interested in. This is the function that is right here in blue that we were trying to find the equation for. Okay, so again, the way that we kind of approach that is we use the graph in blue. We know that for either secant or cosecant, we have these guiding points that kind of help map out the sine or cosine function, the reciprocal trig function. We see these asymptotes would have applied to the zeros of that sine or cosine function. We decided that because we have a maximum here on the y-axis, we decided to use cosine. We found all the transformations. We found the midline, y equals 1, told us there was a vertical shift up 1. The amplitude was still 1, so just still a 1 out front. We found the period was 4 pi, and if the period is 4 pi, that means the b term is 1/2. So then we wrote the equation of our little guiding line, which was cosine, and then we know the reciprocal of cosine is secant, so we switched it to secant. All right, so it's a pretty involved problem. Let's try another one here. So let's do a little bit more of the same. The first thing I think is a good idea is to go ahead and put in our asymptotes. So I can see an asymptote here at pi over 4, 5 pi over 4, 9 pi over 4. There's also one here at -3 pi over 4. Again, all these minimums and maximums are going to be guiding points for us. And it looks like our midline is going to be at -1. Okay, midline's at y equals -1. Let me go ahead and take note of that. So midline, y equals -1. The amplitude, once again, is going to be 1. Again, we can see that from going from the midline to a max, or midline to a min. Amplitude is going to be 1. So let's go ahead and put in all our little guiding points here. Okay, so there's the curve that's going to guide us along. Notice that we don't have anything going through the origin, but we also don't have any maximums here. So it looks like if we would have taken this point, it looks like from the origin it was shifted down and right. So we could have had a point there at the origin, which means I'm probably going to use the sine function. But let's look at the period real quick also. It's looking like our period is going to be from, if we look at one full positive, one full negative section, or we could literally go from here, kind of trace that part, pi over 4 to 9 pi over 4. Well, that's going to be a period of 2 pi. So the period equals 2 pi. And we know for sine and cosine, their parent functions have periods of 2 pi also. So this implies to us that the b is just 1. So the b term has not been changed. But as we noticed earlier, we're going to use sine. So let's go ahead and take note of that. Use sine. And we know that sine starts at the origin, and this is the point we're kind of moving to. So sine was shifted down 1. We can tell that from the midline was moved down 1, but also to the right by pi over 4. So we have a phase shift. Right pi over 4. Okay, so let's go ahead and write out the sine function here that's in the dotted red. So we would have y equals, well, the a term is still 1, so just sine. The b term is still 1, so this is just going to be x. But we have phase shift to right pi over 4, so that'd be minus pi over 4. And then we know we have a vertical shift down 1 because the midline was moved down 1, so we have y equals sine of x minus pi over 4 minus 1. Now, to get the one we're really interested in, we know the reciprocal of sine is cosecant. So the graph therein, it looks like either black or dark green, is y equals cosecant x minus pi over 4 minus 1. All right, so once again, let's go check this with Desmos real quick. Cosecant x minus pi over 4 minus 1. And we're looking for points like negative pi over 4, negative 2. We're looking for points like 3 pi over 4, 0. We'll check one more, maybe 7 pi over 4, negative 2. So that looks good. I'm also just now realizing we didn't check the previous graph, so let's check some points there just to verify. From the previous graph, we want to see some points like 0, 2. We want to see points like 2 pi 0, which we can see, and 4 pi positive 2. We can see that as well. So that graph was also accurate. Okay, let's look at our last example in the notes, and we are going to have a cotangent this time. Let's think about what the parent function of cotangent looks like. Typically, so for the parent function of cotangent, it usually goes through 0, 0. And we can see that here just by looking at the parent function real quick. So here's the parent function of cotangent. But we can see, or sorry, not through 0, 0, but let's zoom in. That 0, 0 is where one of the asymptotes is. What we're seeing here is that we don't have an asymptote at 0, 0. It's looking like instead we have asymptotes that have been shifted to the left by pi over 4. Because if you look at your new asymptotes, let's do this in purple here. We have new asymptotes right here, negative pi over 4. And originally the asymptote was going through 0. So it looks like our asymptotes have been shifted to the left by pi over 4, which means the entire function has been shifted left by pi over 4. Okay, so that's one thing I'm going to take note of. So phase shift. Left by pi over 4. Okay, the period, if we look at our period here, once full cycle, we'll go from asymptote to asymptote, so negative pi over 4 to 3 pi over 4. That's going to be a period of pi, so the period is pi. Remember that for cotangent, the parent function of cotangent already had a period of pi, so that tells us that the b term is the same. B term is still at 1. If we look at the a term, notice that in between each of the asymptotes, is that point in the middle. And if you look at the point in the middle in an asymptote and go in the middle of that, being stretched up to 2. So the A term, which is not an amplitude, but more of a vertical stretch, is 2. So our A term is 2. And that seems to be all that's been transformed here. So let's go ahead and write the transformations here. So we would have y equals, the A term is 2, so 2 cotangent. We haven't had any kind of period change, so still just x. The B term is still 1, but we are shifting left by pi over 4, so this would be x plus pi over 4. There's no vertical shift. We can tell there's no vertical shift because this that point in the middle of the two asymptotes is still at the x-axis, so that hasn't been shifted up or down at all. So there's nothing to add on the outside or subtract on the outside. So this should be our equation. And let's, one more time, go ahead and double check in Desmos. Always a good idea to double check your work here. So we want to look at 2 cotangent, x plus pi over 4. And let's see some of these graphs, or some of these key points. We should see a point at pi over 4, 0. We can see that there. We should see a point at 5 pi over 4, 0. We can see that there. You can continue to verify points if you want. You can also see that they're going up to 2. So 0, 2, you can see that right there. So this is a good graph, nothing wrong, and everything checks out.